Welcome to class number 26 of basic electronics. So we were discussing the MOSFET. So just a little bit recap of the last class. So we basically have this p-type semiconductor block over here, which is known as the body. And then on the top of this p-type body, we basically fabricate a layer of oxide. And if this p-type semiconductor is basically silicon, then this oxide is going to silicon dioxide. Okay, and then on the top of this oxide layer we will fabricate this metal gate. Okay, now this gate and the body are basically biased by a voltage source which we call VGS. Okay, and here we basically fabricate two N plus regions. Okay, here we fabricate two N plus region, and this body is basically shorted with this N plus region, which is known as the source. And then between this source and the drain over here, we are basically connecting another voltage source, VDS. So we can actually compare this VDS voltage with the collector voltage of a BJT, and we can compare this VGS voltage with the base voltage of a BJT. Okay, so VDS is basically like the collector to emitter voltage of the BJT, or VDS is basically analogous to the collector to emitter biasing that we provide in a BJT, and this voltage VGS is basically analogous to the base to emitter biasing voltage that we provide in a BJT. Okay, so initially we would assume that this VDS is 0 and VGS is 0. So under this condition we do not have any, basically no current, no current flow. Okay, so under the condition VDS equal to 0 and VGS equal to 0, there is no current flow. And let me again remind you that this is the source, because this is basically connected to the negative pole of the battery, and source basically emits electrons into the channel, and the drain basically accepts electron from the channel. So this N plus contact, which is connected to the positive terminal of the battery, this is basically known as the drain. Okay, it is connected to the positive terminal of the battery over here. Okay, so when VDS equal to 0 and VGS equal to 0, there is no current flow. Now when VGS is increased, what will happen is that the metal gets a higher potential than this body. This metal gate gets a higher potential than the body. So electric field actually impinge from the metal into the surface of the body in this direction. Okay, if VGS is greater than 0. And this electric field, what they do is they basically repel the hole. So they basically drive away the hole from the surface. Okay, initially when this electric field was not there, or initially when VGS and VDS were 0, then everything was neutral in the body. Now this electric field that is impinging on the surface of the body, that is basically repelling the holes. So when the holes are repelled, or when holes move away from the surface, the negative charge is basically exposed, and this negative charge basically belong to ions. This negative charge is basically not mobile. Okay, so this basically become ions basically. Okay, or in other words, the charge that is developed initially when VGS is increasing from 0, that basically cannot contribute to any current flow because that charge is basically immobile. Okay, so immobile charges from the depletion layer. So initially when VGS is increased, a depletion layer is created near the surface. So we get a depletion layer here, and the width of the depletion layer basically increases with increasing VGS, because more the value of VGS, more is the amount of the exposed charge, because a higher voltage creates a higher electric field at the surface, and a higher electric field would basically repel away more holes. Okay, so we get a depletion layer here near the surface. So this layer is basically depletion layer, and this is negatively charged. Okay, so negatively charged depletion layer. Okay, now when we increase VGS, then this depletion layer grows thicker and more charges are exposed, or more holes are repelled away from the surface. So now the depletion layer contains more charge, and in this way when we keep on increasing this VGS, one point of time would come when all the holes from the surface, that is from this region, has actually been repelled. So if we keep on increasing VGS, more holes are basically repelled away from the surface, and one point of time would come when all the holes have actually been repelled from the surface. Now beyond that point, if we increase VGS, okay, no more holes would further be repelled from the surface because there are no holes at the surface. Now what will happen if we keep on increasing VGS beyond this point is that a very thin layer of electrons would actually be created at the surface, and this thin layer of electrons basically contain mobile electrons. Okay, electric field basically attracts these electrons, and this thin layer of electrons are basically mobile. They are not static electrons, and they do not belong to any particular ions or particular atom. So they are more like free electrons, and these electrons are basically mobile. So a very thin layer of electrons is basically now created at the surface, basically on increasing VGS beyond a certain point. Okay, and the voltage at which the creation of this very thin layer of mobile electrons starts is basically known as the threshold voltage. Okay, it is denoted by VTH. So this is basically the value of VGS at which the thin layer of mobile electrons basically starts forming. Okay, and this is known as the threshold voltage. Okay, so if this VDS is basically 0, and VGS 0 less than VGS is less than VTH, then still again no current would actually flow. Now in this condition also, this 0 less than VGS less than VTH, if VDS is greater than 0, in that condition also no current would actually flow. Okay, if this gate to source voltage or VGS is less than VTH but VDS is greater than 0, then no current would actually flow between the source and the drain, because there is no current flow path, basically the channel is not yet created if VGS is less than VTH. So since the channel is not yet created, therefore on increasing VDS, no current would flow from the drain to the source, or no electrons would flow from the source to the drain. Okay, so now once we cross this threshold voltage VTH, a thin layer of electrons actually starts to form at the surface, and these electrons, just as I stated, are highly mobile, and they basically give the channel or give the surface of the MOSFET a conductance. So now if we increase this VDS or this drain to source voltage slightly, then current starts to flow between the drain and the source, or electron starts to flow from the source to the drain. Okay, so if VDS is greater than 0 and VGS is basically greater than VTH, then current starts to flow between the source and the drain. Why? Because now there is a conducting channel at the surface, and this channel basically consists of mobile electrons, and this channel basically contributes to current flow between the source and the drain. Okay, now if we actually keep on increasing VGS, okay, once we cross the value of VTH and we still keep on increasing the value of VGS, then the number of electrons or the number of mobile electrons which are induced at the surface, that is in this layer, would basically increase, because increasing the value of VGS basically increases the electric field and more electrons are attracted towards the surface. So the number of electrons that are present in this layer or in this channel would basically increase. So the conductivity of the channel will increase. So when VGS is basically greater than the threshold voltage, then the drain to source current would basically increase with increasing VGS, because more electrons would be induced in the channel, and the conductivity of the channel or the conductance of the channel would basically increase when we increase VGS beyond the threshold voltage. Okay, and this layer, this thin layer of electrons which are mobile, this layer is basically called the channel or the inversion layer. And since this layer basically consists of mobile electrons, this is known as a N channel, okay, or N type channel, and from there this kind of MOSFET is basically called an N channel MOSFET. N channel MOSFET in the sense that the channel or the inversion layer basically contains mobile electrons. Actually, electrons have basically a negative charge, and that is why this channel is basically known as N channel. Okay, and from there the name has come, N channel MOSFET. Okay, so once this inversion layer or channel is formed, that is once VGS is greater than VTH, then increasing VGS basically increases the drain to source current for the same value of VDS, because increasing VGS basically induces more electrons in the channel or increases the number of electrons in the inversion layer. Okay, so let me write it here. So once this channel is created, that is VGS surpasses this value of VTH, the threshold voltage, then the drain to source current increases with increasing VGS. This is because increasing VGS increases the electric field at the surface, and so more electrons are induced at the surface. or more electrons are attracted in the inversion layer, or more electrons are attracted towards the inversion layer. So the inversion layer now contains more electrons, and that increases the conductance of the inversion layer or the conductance of the channel. Okay, so it basically makes the inversion layer stronger. Okay, so once the channel is formed, then the drain to source current basically increases with increasing VGS, and this type of MOSFET is known as N-channel MOSFET. Because the inversion layer or the channel contains electrons which are negatively charged. Okay, so now let us understand, if this VGS is greater than the threshold voltage, that is the channel is already formed, in that case how the drain current would basically vary with the drain to source voltage. So on the horizontal axis here we draw the drain to source voltage VDS, and in the vertical axis here we draw the drain to source current IDS. Okay, so if you don't remember, let me show you this diagram again. That VDS is basically the voltage that is applied between the source and the drain. So VDS is basically the voltage that is responsible for creating the horizontal electric field in the channel, due to which the electrons would move from the source towards the drain. Okay, and IDS is basically the current that is flowing from the source to the drain. So this current over here is basically IDS. Okay, IDS is the current that is flowing from the drain to the source. Okay, so once this channel is actually formed, or once the inversion layer is actually formed, so we have a conductive path beneath the surface or at the surface, and that is why the current would basically increase with increasing VDS. So initially, for small values of the drain to source voltage, this channel basically behaves as a linear conductor. Okay, so the current basically increases linearly with increasing VDS. Okay, so the current is increasing linearly with increasing VDS. Now this VGS, the function of this voltage VGS, is basically to create the vertical electric field in this direction, and this electric field basically induces the inversion layer of the channel. Okay, now to induce this channel, the potential difference between the gate metal, that is, let us consider this point at the source end, this is the gate metal, the potential difference between this point over here, which is the gate metal, and this point, which is the body, should actually be greater than the threshold voltage. Now this body is basically shorted with the source. Okay, and so the source is basically controlling this voltage at this point. Okay, since the body is shorted at the source is basically controlling the potential at this point. Okay, this point is basically attached to the source, that is the extreme left part of the channel. The extreme left part of the channel, that is this point over here, is basically attached to the source. This part is the source, and the extreme left part of the channel is attached to the source. So it is obvious that this part of the body, which is attached directly with the source, is going to have the source potential. Okay, and this channel is induced if the potential difference between this point here at the metal gate and this point here, which is attached to the source, is basically greater than the threshold voltage. Okay, that was the condition, that the potential difference between the metal gate and the body must be greater than the threshold voltage. Okay, so once this potential difference between this point and this point is greater than the threshold voltage, the channel would basically be induced at the source end. Okay, that is at this part. Okay, now the channel is basically induced at the source end when the potential difference between the gate and the potential difference between the source is basically greater than the threshold voltage. Okay, which implies that VGS is basically greater than the threshold voltage. So this is the condition at which channel is induced at the source end. Now, when VDS was equal to 0, or the source and the drain was shorted, in that case the potential at the drain would be equal to the potential at the source. So under such a condition, the channel at the drain is induced whenever the channel at the source is also induced. Now, if VDS is actually greater than 0, in that case the potential at the drain is not equal to the potential at the source. Under such a condition, the channel at the drain end would be induced when the potential at this end, that is the metal gate, and the potential difference at this point, which is basically the part of the body which is attached to the drain, is greater than VTH. Okay, I again repeat that when VDS is not equal to 0, in that case the potential at the drain is not equal to the potential at the source. So under such a condition, the channel would be induced at the drain end when the potential difference between this point over here and this point, which is basically the part of the body which is attached to the drain, is basically greater than the threshold voltage. So channel is induced at the drain end when the potential difference between the gate and the potential difference between the drain is greater than VTH, because the part of the body that is attached to the drain, that is this part, or the part of the body that is near the drain, is going to take the potential of the drain. Okay, so near this part or the extreme right, channel would be induced when the potential difference between the gate and the drain should be greater than VTH. So we can actually write this as VG minus VS minus VD minus VS is greater than VTH, which basically implies that VGS should be greater than VDS minus VTH. Okay, if this condition is not met, in that case there is no channel induced at the drain end here. Okay, so this channel would in that case simply look like this. So if this condition is actually not met, in that case the channel would simply look like this. So where the channel is induced at the source end and the strength of the channel basically decreases as we gradually move towards the drain end, and then at the extreme right there is actually no channel. This condition is basically known as pinch off. Okay, the condition under which at the extreme right end or at the drain end there is no channel or there is no inversion there, this condition is known as pinch off, and this region is basically known as the pinched off region. So pinch off. Okay, and I again repeat that channel is induced at the drain end when this condition is basically made, that VGS is greater than VDS minus VTH. Okay, now let us take this figure, this channel here. I have shown it to be wider at the source end and thinner at the drain end, that is this portion. This is just to show that this part of the channel which is attached to the source end basically contains more number of the electrons actually. Okay, this is not really the thickness of the channel that is varying, but it is actually the number of electrons or the strength of the channel that is decreasing as we move from the source towards the drain. Okay, and this part of the channel actually contains more electrons, that's why it is shown thicker, and then as we gradually move towards the drain end, the channel is becoming thinner, which basically means that the number of induced electrons is basically less. Okay, it is not actually that the dimension of the channel becomes thin, but a thinner channel basically means that the number of electrons induced is basically less. And at the extreme right end, where this portion there is no channel, so basically this region is known as pinched off region, and this region basically contains depletion charge. And the condition that is needed for inducing a channel at the drain end is basically VGS greater than VDS minus VTH. Okay, now let us assume that this definition is met, and this condition is basically made, that VGS right now is greater than VDS minus VTH. Okay, so initially let us assume that VDS is basically 0. So if VDS is basically 0, so in that case the channel is going to have equal strength at the drain end and the source end, or the channel is going to have the same density of electrons at the drain end and the source end. Okay, so initially VDS was 0, the channel is uniform everywhere. Okay, now initially when VDS is increasing, remember that the potential difference between this point and this point is basically responsible for creating the channel. Okay, and higher the potential difference between this point and this point, the channel is going to be stronger at the drain end. Okay, so if the potential difference between the metal gate at this point and the body at this point, which is attached to the drain, is actually greater, then it is going to induce a stronger channel, or it is going to induce more number of electrons in the channel. On the other hand, if the potential difference between this point and this point, or if the potential difference between the gate and the drain becomes less, then the strength of the channel basically becomes less, or the number of electrons that is induced at the drain end of the channel, that becomes basically less. Okay, so initially when VDS is increasing, let us assume that initially we had actually applied a voltage VGS which is greater than VTH. Okay, so we have applied a gate to source voltage which is greater than the threshold voltage. So the inversion layer is induced here at the source end of the channel, and there is also an inversion layer at the drain end of the channel when VDS is equal to 0. Okay, and when VDS, or the drain to source voltage, is equal to 0, in that case the strength of the channel, or the density of electrons at the source end of the channel and the drain end of the channel is basically the same. Now we are increasing VDS, so the potential at the drain end of the channel is basically increasing. Okay, so if the potential at the drain end of the channel increases, then which basically means that the potential at this point is basically increasing, and if the potential at this point increases, in that case the potential difference between the metal gate and this drain end of the channel basically reduces. I repeat again that if the potential at the drain increases, then the potential difference between the gate and this part of the body which is attached to the drain basically decreases. So if the potential difference between this point here and this point here basically decreases, then the strength of the induced channel at the drain end also decreases. So initially when VDS is increasing, in that case the strength of the induced channel at the drain end would basically decrease. Okay, so in that case we still have a channel at the drain end, but the strength of the channel at the drain end has basically decreased when we increase VDS, and that is why the channel is shown to be thicker at the source end, which basically means that the channel at the source end has a higher density of electrons, and the channel is shown to be thinner at the drain end here, which basically means that the channel at the drain end contains a lower number of electrons. Okay, so when we increase VDS, this basically means that the strength of the inversion layer, or the number or the density of electrons in the inversion layer at the drain end of the channel basically reduces. So this basically means that the overall strength of the channel, or the average conductance of the channel, is also reducing. Okay, if the conductance or if the strength of the channel at the drain end reduces, then this means that the overall or the average strength of the channel also reduces, because the average conductance or the average strength of the channel is basically the conductance, the average of the conductance of all the points within the channel. So if the conductance of the channel at the drain end basically reduces, this basically means that the average strength of the entire channel basically reduces. So when we keep on increasing VDS, initially for small values of VDS, the current increases linearly, but as we keep on increasing VDS, just as I said, that the strength of the channel or the density of electrons at the drain end of the channel basically reduces. So current would not increase as fast as before with the drain to source voltage, but the rate of increase of current with the drain to source voltage basically reduces. Okay, so the slope of the current versus voltage graph basically decreases. Okay, now just as I stated earlier, that until this condition is valid, till that point there is some inversion layer, or there is some inversion electrons, or there is some channel which exists at the drain end. If we keep on increasing VDS, then one point of time would come when VDS would increase so much that this condition would no more be valid. Okay, so I repeat again that if we keep on increasing this VDS, because we have kept VGS constant, if we continue to increase VDS, then one point of time would come when this condition is not valid anymore. Okay, and under such a condition, just as I stated, that the channel near the drain end would basically vanish. Okay, so under such a condition, this channel near the drain end basically vanishes like this. Okay, there is no channel at the drain end. There is some channel at the source end, and then the strength or the density of electrons in the channel decreases as we move towards the drain end, and exactly at the drain end there is no channel. So this condition is known as pinch off, and this region where there is no channel at the drain end, this region basically contains depletion charges. Okay, so let me write it here, that if we keep on increasing VDS, the strength of inversion layer will decrease at the drain end. Further, on further decreasing VDS, one point of time would come when VGS when the condition VGS is greater than VDS minus VTH is not valid anymore. In that case, when this condition is not valid anymore, the inversion layer disappears at the drain end, and this condition is at the drain end. This condition is known as pinch off in case of MOSFET. Okay, so once this VGS, if we keep on increasing this VGS, just as I stated that the strength of inversion layer at the drain end basically decreases, so the average strength of the channel basically decreases, so the current would not increase as fast as before on increasing VDS, but the rate of increase of current with VDS basically slows down. And then once this condition is met, that once this condition VGS equal to VDS minus VTH, once this condition is made that VGS equal to VDS minus VTH, the channel just disappears at the drain end. Okay, VGS greater than VDS minus VTH denotes that a channel is induced at the drain end, or the drain end has a channel. Then when we increase VDS, this condition is met, VGS equal to VDS minus VTH, and when this happens, the channel just disappears at the drain end, and then this pinch off condition is basically made, or the channel is basically pinched off, and this happens for VGS equal to VDS minus VTH. Now if we further increase the drain voltage, okay, if we further increase the drain voltage, what happens is that at VGS equal to VDS minus VTH, the channel is pinched off, so no channel exists at the drain end, and the drain end is actually exposed to the depletion charge. So if there is no channel at this end here, there is basically depletion charge here. Okay, so depletion charge is basically exposed at the drain end when VGS is equal to VDS minus VTH. Now when we further increase the value of VDS, then this voltage the value of the drain to source voltage at which this condition is basically made is known as the saturation drain to source voltage. Okay, the value of VDS at which the channel just pinches off, or the channel just disappears at the drain end, that is this condition VGS equal to VDS minus VTH is satisfied, is known as the saturation drain to source voltage. And this is denoted by VDS sat. So VDS sat is basically equal to VGS minus VDH. So VDS set is basically a fixed voltage, and it is the voltage at which the inversion layer just disappears at the drain end, or the drain end of the channel just pinches off. Okay, so if we further increase the drain to source voltage beyond the saturation voltage, what happens is that this extra voltage VDS minus VDS set basically drops across this very small pinch of region. Okay, because this region contains depletion charge. This is not a conductive region. Okay, this region contains depletion charge. This is not a conductive region, and we already know that the depletion region can actually withstand very high electric field, or there is very high electric field in the depletion region. This we have already learned when we are studying the PN junction. Okay, so when this VDS increases beyond VDS set, in that case the extra voltage VDS minus VDS set basically drops in this region which contains no channel. Okay, and this part of the channel where it just pinches off, that is this point over here. Okay, I will just circle it in a bigger way so that it is visible. This point of the channel where the channel ceases to exist, or this point where the channel just pinches off, this point has basically a voltage which is equal to VDS set. So this point has the voltage VDS set, and the extra voltage, that is VDS minus VDS set, provided that VDS has become higher than VDS set, this extra voltage VDS minus VDS set, this extra voltage basically drops across this very small depletion region where the channel has ceased to exist, or this voltage basically drops across this very thin or small depletion region which is basically exposed, or where there is no channel. Okay, so basically this part. So this part basically contains this voltage, or holds this voltage VDS minus VDS set. Okay, now when we increase this voltage VDS, what happens is that this point where the channel has just pinched off, or where the channel has just ceased to exist, this point slightly shifts towards the left. Okay, because increasing VDS basically increases the electric field, and we need a thicker exposed depletion region, that is we need a thicker region where the channel has ceased to exist to hold this voltage VDS set. Okay, repeat again that once this VDS increases beyond VDS set, if we further keep on increasing VDS, in that case this region where the depletion region has ceased to exist, that is this region, actually needs to become thicker in the horizontal direction, or thicker in the or wider in the horizontal direction, to basically hold the excess value of VDS. And that is why this point here where the channel has just pinched off would actually shift slightly towards the left, and this width and this width of the depletion region here, which is exposed now, or which is devoid of any channel, this width in the horizontal direction of the exposed depletion region basically has to increase to hold this excess value VDS minus VDS set if we increase VDS. Okay, so this part of the channel, or this point of the channel where the channel has just become pinched off, that needs to shift slightly towards the left to incorporate or to hold this excess voltage VDS minus VDS set. So once this channel becomes pinched off, just remember that the point at which this channel is just pinched off basically has the same voltage, and the voltage at the point at which the channel has just pinched off, the voltage at that point does not increase with increased VDS once the channel has pinched off. Okay, so this basically means that if the point at which the channel has just pinched off has the same voltage irrespective of the value of VDS, then the average electric field across this conductive channel would basically be the same, and the excess electric field VDS minus VDS set would basically drop in this region which is devoid of any channel, or where depletion charges have basically exposed itself. Okay, now since the average electric field through the channel is constant once the pinch off condition is reached, or once VDS is higher than VDS set, therefore the current that flows through the channel would basically be constant because the average electric field through the channel is constant. Now the question is that since there is no channel in this region where depletion charge has exposed itself, or where there is no channel, okay, since there is only depletion charge in this region, how would current flow through this region? So the answer is that in this region where the channel still exists, here the current is basically conducted by the channel. Okay, now when the electrons reach this point where there is no channel, beyond this point the electrons flow due to a very high electric field which exists across this exposed depletion region here. Okay, this exposed depletion region, as we know, contains a very high electric field, and when the electrons reach the end of the channel or the pinch off point of the channel, that is this point over here, once the electrons reach this point, beyond this point electrons flow due to a very high electric field that exists in the exposed depletion region. Okay, so current flow across this exposed depletion region is actually like the current flow in a reverse biased PN junction. Okay, so this region where the depletion region is exposed, or where there is no channel, this region doesn't basically have any electrons of its own or any induced electrons of its own, but it has a very high electric field, so it basically transports the electrons or transfer the electrons which the channel can provide it from the left. Okay, so this region where there is no channel, this region basically transfers the electrons from the point at which the channel is pinched off to the drain. Okay, because there is a very high electric field. So this region over here does not have a conductance of its own, but it only transports or transfers the electrons that the channel actually supplies it from the left. Okay, and just as I stated that because the potential at the pinched off point, that is at this point here where the channel just pinches off, since the potential at this point does not change anymore with increasing VDS once the pinch off has reached, therefore the potential difference across the channel is effectively VDS set. Okay, because at this point the potential is basically that of the source, and we can assume the source to be grounded, so the potential at this point is basically 0, and the potential at this point is basically VDS set over here. So the potential difference across the entire channel is effectively VDS set. Okay, since the potential difference across the entire channel is approximately VDS set once pinch off is reached, therefore the average current that is conducted by the channel is basically constant once pinch off is reached, because the potential difference across the channel is basically constant. So once pinched off is reached, in that case the current at the drain or the drain to source current does not increase anymore with increasing VDS, because the potential difference across the channel is effectively constant at VDS set. Okay, so the current does not increase anymore with increasing VDS. So this voltage at which pinch off is reached, or after which the current is effectively constant, this voltage is basically known as the pinch off voltage or the saturation voltage, and this is basically denoted by VDS set. And VDS set is equal to VGS minus the threshold voltage VTH. Okay, now we see that if we keep on increasing this value of VGS, in that case the effective value of VDS set would basically increase. And we also know that if we basically increase this value of VGS, then the conductivity of the channel is also going to increase, because increasing the value of VGS basically induces more electrons in the inversion layer, or increases the average density of electrons in the inversion layer. Okay, so this is, let us say, for VGS 2. Now if we decrease the value of VGS, one point is that this saturation value of VDS would actually reach at a lower value, because if we decrease VGS, then saturation would actually basically reach at a lower value. So if we basically decrease VGS, then saturation would basically reach at a lower value. So let us say at this value my saturation VDS is reached now. So VDS1 set is equal to VGS1 minus VTH. This is VDS2 set, which is equal to VGS2 minus VTH. Okay, so now the saturation is to reach at a lower value of VDS, and another point is that if we decrease VGS, then it basically decreases the average number of induced electrons in the channel. Okay, so if we decrease VGS, then the average number of induced electron in the channel basically decreases. So the current, or the maximum value of the current, is going to become lower. So this curve is for basically VGS2, VGS1. Again, if we increase the value of VGS beyond VGS2, in that case, again we would reach saturation or constant value of current at a higher voltage. So let us say this is VDS3, VDS set 3, which is equal to VGS3 minus VTH, and VGS3 is actually greater than VGS2. So VGS3 is greater than VGS2, which is greater than VGS1. Okay, so now my saturation or constant value of current would be reached at a higher voltage, and because I have increased the value of VGS, this basically means that the average number of induced electrons in the channel is now higher, because VGS has become higher. So my saturation current, or the value of the constant current, is basically going to increase. So this is for VGS3. And all of this VGS1, VGS2 and VGS3 are basically greater than the threshold voltage VTH. Okay, and this region where the current becomes constant with the drain voltage, or the current effectively does not increase anymore with the drain voltage, this region is basically known as the saturation region, or the saturation regime. Okay, so the right portion or the regime to the right of this black dashed curve basically denotes the saturation regime, and the regime to the left of this black dashed curve is known as basically the triode regime. Okay, so the dependence of the MOSFET drain to source current on the drain to source voltage is related by the equations which we will now write, and we'll not again derive this equation here, but I'll just write it here. So IDS is equal to 0 for VGS less than VTH. So for any value of VGS which is less than the threshold voltage, irrespective of what the drain to source voltage is, the current is always 0. Okay, and IDS is equal to Kn, where Kn is basically a constant for a MOSFET, to VGS minus VTH VDS minus VDS square for VGS greater than the threshold voltage and the triode regime, and the triode regime is basically given by VDS less than VGS minus VTH. Okay, so this is the triode regime basically, where the current is still increasing with the drain voltage, and it is actually clear from this equation over here that there is this VDS and there is this VDS square. So the current is still changing with the drain voltage, and this is for the triode regime where the current is still changing with the drain voltage, and IDS is basically equal to Kn VGS minus VTH square once we reach the saturation regime, that is for VGS greater than VTH and VDS greater than equal to VGS minus VTH. Okay, so this is basically, I repeat again, this is known as the saturation regime, and in this regime the current does not increase anymore with the drain to source voltage. Okay, and Kn is constant for a given MOSFET, and Kn is basically given by the equation mu n W by L divided by 2. So basically mu n W by 2L into Cox. Okay, where Cox is basically the oxide capacitance per unit area. So oxide capacitance per unit area is basically epsilon ox divided by Tox, where epsilon ox is basically the permittivity of the oxide layer, and Tox is basically the thickness of the oxide layer. So Tox is basically the thickness of the oxide layer. So basically this thickness of the oxide layer is basically Tox. Okay, now W is basically the channel width. And it is obvious that if the width of the channel increases, then the current also increases. So width is basically perpendicular to the plane of the paper. So this MOSFET also has a dimension like this, a third dimension. We have actually shown it in 2D, but if we actually draw it in 3D, it would basically look like this. Okay, and this source and drain basically extends in this direction. So W is basically the thickness, the width of the channel. So W is basically the width of this channel in this dimension over here. Okay, and it is obvious that if we increase the width of the channel, or if we increase the width of the MOSFET, of course the current is going to increase because the number of electrons in the channel basically increase. The density of electrons in the channel remains the same, but if we increase the width, the number of electrons in the channel would increase, and so the conductance of the channel would basically increase. Okay, so this is basically our width of the channel, and L is basically the length of the channel. L is basically channel length, and this is effectively the distance between the source and the drain, or approximately equal to the distance between the source and the drain. So the channel length is basically this length over here. So the channel length is basically this length, or the distance, effective distance between the source and the drain. Okay, so and it is obvious that the current or the conductance of the MOSFET would basically decrease with increasing the channel length, because VDS set is basically constant. So increasing the channel length basically means that we are decreasing the average electric field within the channel. Okay, so if the average horizontal electric field within the channel decreases, this basically means that the current would basically decrease. Okay, so this is basically the current voltage relation of the MOSFET, and we have three regimes for the MOSFET. One is the VGS is less than VTH, and this regime is known as the cutoff regime, basically similar to a BJT. The cutoff regime in a BJT is basically the regime where the base to emitter voltage is lower than the cut-in voltage of the base to emitter diode. In the MOSFET also, the cutoff regime is the regime where the gate to source voltage is less than the threshold voltage. Okay, and then comes the triode regime, where the drain to source voltage is basically less than VGS minus VTH, and then comes the saturation regime, where the drain to source voltage is basically greater than VGS minus VTH. So we have three regimes here. So for a fixed value of VGS, if we basically increase VDS from 0, in that case initially no current would actually flow. Okay, so initially the regime is the triode regime, and then if we keep on increasing VDS, we would basically reach saturation regime. On the other hand, if VDS is basically fixed and greater than 0, and VGS is varying and increasing from 0, in that case initially when VGS equal to 0, we have the cutoff regime, and then as we increase VGS, we reach the saturation regime, and then when we further increase VGS, we reach the triode regime. Okay, so let us do up to here today. So thank you everyone.